Hello, SL2. Today's topic is applications of logarithmic and exponential functions. Our essential question today is, can I apply my knowledge of the following applications to logarithmic and exponential functions? We will be applying it in ways that we already know, including taking the tangent and normal, or finding the tangent and normal, finding the rate of change, curve properties, displacement, velocity, and acceleration, and optimization. Tonight we're going to be looking at two IB questions and that are related to applications of log and exponential functions. Our first example is a 7-point question, and we have our g of x is equal to the ln of x divided by x squared for all x values greater than 0. Our first part, A, is asking us to use the quotient rule to show that the first derivative is equal to 1 minus 2 ln of x divided by x cubed. So in this case, we cannot use the product rule. I know several students sometimes like to change a quotient into a product, but for this example, we would not receive credit if we did that. We must show finding the derivative with the quotient rule. So let's take the derivative of our g of x in part A using the quotient rule. Our quotient rule, remember, our u would be our numerator and our v would be our denominator. Our derivative of u, in this case, will be 1 over x. Remember, when you take the derivative of the ln of x, you're going to take the inside down the denominator and then take that derivative and put that in the numerator. So in this case, we'll bring the x down, and then the derivative of x is 1. The derivative of v, x squared, would be 2x. When we use the quotient rule, we take our derivative of u times our v minus our derivative of v times u, and we put it all over v squared. So let's go ahead and do that. So if we have the derivative of u, 1 over x, times x squared, our v, minus our derivative of u times our ln of x, our u. And that is all over v squared, which would be x squared to the second power. We can quickly see several things to simplify. First is this exponent here, x squared divided by x, would simplify to x. And then in the denominator, x squared squared would be x to the 4th power. Okay, once I finish taking my derivative using the the quotient rule, I'll go ahead and look up to what they want me to prove it to be. Here I can see, okay, they want us to factor out another x so that it is more simplified. And I saw that by just looking at the denominator was only x cubed, and I can quickly see that there's a common factor of x. So let's go ahead and do that. But we're factoring out that x. I should not have written that again. Now we can cancel one of those x's since it's multiplying here. Remember, we can only cancel when it comes to fraction when we're multiplying two things with the denominator. So here, one of those x's would cancel with one down here, and we'd be left to the third power. So our first derivative we proved is 1 minus 2 ln of x all over x to the third. Okay, let's see what part B brings. Part B tells us that the graph of g, our original function, has a maximum point at A. They want us to find that x-coordinate of A. So going back to our optimization, anytime they want us to maximize, we'll take the derivative and set equal to 0 to find our value. Lucky us, we've already taken the derivative, so all we have to do is set this derivative equal to 0. You would want to show that knowledge, the derivative of x be equal to 0 for the maximum, and set the first derivative to 0. When it comes to a rational expression, setting equal to 0, we only have to show when the numerator is equal to 0. So we're solving for x. First step, I'm going to add 2 times ln of x to both sides. Again, we're trying to solve for x here, so I'm just isolating x as much as I can. And we get the ln of x equals 1/2. Now, when we're, remember back to Algebra 2, and I believe you did a lot of this last year in SL1, but when you're trying to get to this x, the best way is converting it back to exponential form. So remember what the natural log means. It's the log base of x. And then remember how we solve for x in this case. You take the base and you set it equal to the exponent. To find the x. So just bringing back that how to solve logarithmics. So the base to this is the exponent, would be equal to x. So our final answer for the x-coordinate would be e to the 1/2. We do not have to find the y value. If we did, we would plug that back in to our g of x. Okay, one more problem, IB problem, and this one is showing some curve properties. So the following diagram shows the graph of my function equal to e to the negative x squared. We have a graph, and it states the points A, B, C, D, and E lie on the graph of f. And 2 of these are points of inflection. So one thing just to remember about that vocabulary, a point of inflection, that is a point on a curve at which the change of the shape occurs. So we're looking for when the concavity changes, because they want us to find, they identify the 2 points of inflection. So those points would be here, B and D, because our here it's concave up, and then at this point B it becomes concave down. At D it becomes concave up again. So this Part A is only identifying. You don't have to show any work here, but you do have to write down the 2 points of inflection of B and D. Now part B is asking us to find the derivative of our function. So our derivative of our function is e to the negative x squared. Our derivative, let's rewrite our function. Our derivative, remember when we're finding for exponential, is the same thing it's written down. And then we take the derivative of our exponent. So negative x squared, the derivative of that would be multiplied by our e to the negative x squared. So that would be negative 2x. So our first derivative is negative 2x e times e to the negative x squared. Okay. Our part 2 of B asks us to show the second derivative is equal to this. So we're just going to keep going. I'm going to go ahead and find some more space down here with part B2 and take my first derivative and find the second derivative. So here we now have a product because we have negative 2x times e to the negative x squared. This is not a number anymore, so this is at one function times another, so we'll have to have a product. Use the product rule here. Our u in this case would be negative 2x, and my derivative of u would be negative 2. My v in this case would be e to the negative x squared, and my derivative of v would again be the entire original item times the derivative of my exponent, so times negative 2x. So we can simplify that by moving the negative 2x in front. So my product is my derivative u times v plus my derivative v times u. So negative 2x times negative 2x is 4x squared times e to the negative x squared. Alright, let's look up and see how we're doing on our proof. Okay, so they want us to prove, and it looks like they want us to factor out that e to the negative x squared. So let's go ahead and do that. And we have negative 2 plus 4x squared. Now our proof has the factored e to the negative x squared on this side, and they switch the order here, so it's 4x squared minus 2. So I'm just going to use my commutative property to help make that be proved completely and show that in the same order as they asked me to. So 4x squared minus 2 times e to the negative x squared. So there's part B. Alright, let's see what C says. So C asks us to find the x-coordinate of each point of inflection. So we need to find the x-coordinate of B and D. So how can I do that? Remember, our point of inflection is found when our second derivative is set equal to 0. So a lot of times the IB questions lead one step into the other. So if you ever get stuck, go back and see if you can use the part in front to help you remember what to do. In this case, it does lead directly in there, but do make sure you're understanding the question. It doesn't always. So here we're going to, in the next part of our video, we will finish part C and